Okay, let's talk about the section 5.2, Riemann sum. So we already discussed the integrability, but that was defined by the upper Riemann sum and lower Riemann sum. And there's another way which possibly is more standard in, or not common, which is more common in elementary calculus. Okay, so we're going to study the so-called standard Riemann sum. And it's not the definition of a standard. There's no standard word, but it's commonly introduced in the calculus textbook. What the Riemann sum is the following. So definition 5.17, f is a function from AB to R. First, the Riemann sum of f with respect to a partition P. Remember, partition means x0, x1, xn of AB is a sum of the form sigma f of tj xj minus xj minus 1, j is from 1 to n, where the choice of tj in xj minus 1 xj is arbitrary. Okay, so this is the Riemann sum. So it's very similar to the upper Riemann sum and the lower Riemann sum. In the upper Riemann sum and the lower Riemann sum, you're going to replace this by either the maximum or the minimum. You choose those special values for the product. And here, the regular Riemann sum, you just randomly pick up a point and evaluate the function at this point. Okay, so this is the Riemann sum without the upper and the lower. Second, we say the Riemann sum of Riemann sums of f. So you see here, even when you have a fixed partition P, you may change your, we can call it sample point. You may change your sample point. So the Riemann sum with respect to a single partition is not unique. The Riemann sum with respect to a single partition is not unique. It also depends on the selection of a sample point. Okay, so there are a lot of Riemann sum. The upper Riemann sum and lower Riemann sum only depend on the function and the partition, because once you fix a partition, you will have the unique supremum or infimum over each subinterval. Okay, so the upper Riemann sum and lower Riemann sum only depend on the partition, but the regular Riemann sum depend on the partition plus the choice of a sample point. Okay, so the Riemann sums of f are said to converge to some number. This number we call it I of f as the norm of the partition approaches 0 if and only if given epsilon greater than 0. Whenever you see the convergence, it's always related to the epsilon delta, epsilon capital N stuff. There is a partition P sub epsilon, this partition depends on this epsilon, of AB such that For any partition P is x0, x1, xn, which is finer than P epsilon. Finer means it contains the P epsilon as a subset of partitions. For any P finer than P epsilon, it implies the absolute value of the difference of Riemann sum. This is a Riemann sum, and this given value IF, this is some specific value. This absolute value of the difference is going to be less than epsilon for all choices of Tj in the interval xj minus 1 xj. So you can choose whatever sample point. This absolute value of difference is always less than epsilon. Here j is from 1 to n. Okay. So for any epsilon, you can find a partition. It should be chopped small enough, sufficiently small, so that whenever a finer partition, even smaller partition, even better partition, will imply the absolute value of the difference is less than epsilon for whatever choice of a sample point. Okay, so this is the definition of Riemann sum converges to some number. Okay, and we write this IF as a limit. The norm of partition approaches 0, sigma f of Tj, xj minus 1, j is from 1 to n. Okay, so that's a writing, and this is a meaning of this limit. Okay, good. So this is the convergence of the Riemann sum. And we learned that the integrability and the integral of the function with respect to a partition and a similar formula. And the next theorem, we're going to show that the IF is actually the integral of the function when it is integrable. Okay, so actually we're going to show that we define two stuffs. Those two stuffs are equivalent. So let A be in R with A less than B. And suppose that F from AB to R is bounded, because we always discuss the bounded functions. So first of all, here the Riemann sum, this argument does not require F to be bounded. So here we never mention F is bounded or not. We use this limit process. But in the integrability, the upper Riemann sum, lower Riemann sum, in that argument, we need this boundedness. Okay, this part, no boundedness, but the integrability part requires a boundedness. Okay, so that's why we require F to be bounded. Then F is Riemann integrable. Remember what is Riemann integrable? For every epsilon, there is a partition so that upper sum minus lower sum is less than epsilon. That's integrable. Riemann integrable on AB if and only if the IF, which is the limit partition approaching 0, sigma j from 1 to n, ftj, xj minus 1, this limit exists. Okay, integrability is equivalent to the existence of this I of f. Okay, in which case, in the case they either it is integrable or the if exists, in which case the I of f is equal to the integral from a to b fx dx. The integral is a supremum of the lower sum and the infimum of the upper sum. Remember that. Okay. So this quantitative statement, this is a property statement. Right? So we are going to prove this 5.18 in detail. Okay. Proof. So there's two directions, if and only if. So first, suppose that f is integrable on AB. F is integrable on AB. And given epsilon greater than 0. Given epsilon greater than 0. We need epsilon greater than 0. Okay, so integrability means there is a partition. We also call it P epsilon of AB such that, okay, so integrability, you will have the lower sum of f with respect to this epsilon is greater than the integral fx dx minus epsilon. Remember, the integral is a supremum by the approximation property. Whenever you subtract supremum by some epsilon, there's an element greater than it. And the upper sum is decreasing. It's infimum, so it's going to be less than f integral fx dx plus epsilon. It's infimum. Whenever you add something, add the infimum by epsilon, definitely there's some element smaller than it. Okay, this is the approximation. Property. And also remember that this integral, it is already integrable. Integrable means these two quantities. It is supremum. It is also the infimum. And these two properties are from this definition of supremum and infimum. Okay, good. Let's check. We are going to verify. We're going to verify what? We're going to verify this IF exists, and actually this IF is going to equal. It's going to be equal to this integral. Okay, so for any partition finer than P epsilon, so for any partition finer than P epsilon, okay, better, even better. Lower sum is increasing, upper sum is decreasing, so we have it's let's make it complete. And upper sum is decreasing for whatever partition containing this. Okay, so for any choice of Tj in xj minus 1 xj. Let's compute this Riemann sum. This is a Riemann sum. The Riemann sum, of course, this is positive. This one is a positive. I'm going to replace it by the supremum, so it's going to be less than or equal to the upper sum. If I replace it by the infimum, it's going to be greater than or equal to the lower sum. Correct? So for arbitrary choice Tj in the subinterval xj minus 1 xj, we always have this. In this one, it is less than integral ab fx dx plus epsilon greater than integral ab fx dx minus epsilon. So we get this Riemann sum bounded by these two quantities, and you subtract integral from a to b fx dx from three sides, you will get absolute value of ftj xj minus 1 minus the integral from a to b fx dx is going to be less than epsilon. Absolute value is equivalent to the difference is bounded by negative epsilon and positive epsilon. Okay, so this is an even only if case. Okay, so if we summarize what we have proved, we will see that, where's the proof? The proof is here. For any epsilon, there is a partition. For any partition containing p epsilon, and for any choice of Tj, we always have this condition. So the IF, which has the precise formula, exists, and it exists and satisfy the condition, right? So that's from the integrability to this to the existence of I of f. Existence of I of f. Okay, that's all. One direction. Let's prove the other direction. Prove the other direction. The other direction we suppose conversely. We suppose that the Riemann sums of f converges to I of f. Okay, converges to I of f. Then it means given epsilon greater than 0, by the definition, there exists a partition p epsilon of AB such that for any partition p finer than p epsilon and any choice Tj in xj minus 1 xj, we have absolute value sigma j from 1 to n ftj xj minus 1 minus fi is less than epsilon. So we just rewrite this stuff. Okay, let's see. In the textbook, they divide the epsilon by 3. It does not matter. It's not important. Okay, so we just first see something, see the stuff, and later you will see if you modify this epsilon by multiplying it with a proper coefficient, you can make the final epsilon looks better, but it's not the important step. Okay, so for each remember we have the supremum over jth interval and the infimum over jth interval. They are supremum and infimum. There are Tj and Uj in the corresponding subintervals such that what? This is a supremum. Supremum means Ftj is going to be greater than the supremum minus epsilon. And Fuj is going to be infimum. Infimum is less than mj plus epsilon, right? Supremum one here is greater than less than or equal to mj. This is greater than or equal to little mj. That's an approximation property of the supremum and infimum. Okay, well, this part is not important, so that's why in the book this part is not included. Okay, so we're going to use Ftj to subtract Fuj is going to be greater than capital Mj minus little mj and minus 2 epsilon. Use this one to subtract this one. Okay, so this is the property we need. All right. Okay, so we have this difference property. Then let's see the upper sum minus the lower sum. Upper sum minus lower sum. It is equal to sigma j from 1 to n mj minus little mj xj minus 1. And this one is going to be less than this difference and plus 2 epsilon. So it's less than sigma j from 1 to n ftj minus fuj and xj minus 1. And here plus 2 epsilon. 2 epsilon times this one is a telescoping, so it's a b minus a. Remember this? So it's a sigma j from 1 to n 2 epsilon xj minus 1. It is equal to it. It's not too difficult to see. All right. Okay, so what we are going to do, we're going to insert IF. We're going to insert IF. Remember, we assume IF exists. So subtract IF and plus IF. So we will have you see this is different, so we get this and subtract IF. And then insert IF minus sigma j from 1 to n fuj xj minus 1. And plus this 2 epsilon b minus a. 2 epsilon b minus a. And remember that all these this inequality always hold. X is less than or equal to ups value of x. So I'm going to consider this as one quantity, this is as one quantity. So here it's less than or equal to, remember that here, for whatever partition containing this p epsilon, this ups value is always less than epsilon. So once I put absolute value and ups value and the 2 epsilon b minus a, I just put ups value for these two terms. And this one is going to be less than epsilon plus 2 epsilon times b minus a. So if you want, you can get 2b minus a epsilon. if you want to make this better, at the original part, for whatever place, you just divide by 2 plus 2 times b minus a, then this is epsilon. But it's okay. So the difference is always less than this quantity than by the definition. So f is integral. F is integrable, right? F is integrable, and once it is integrable, this IF is equal to this the integral, right? You go back to the first one. So what do we get? We do have that the Riemann integrable, or the existence of this limit of the Riemann sum is equivalent to the Riemann integrability, and they actually equal to the same quantity. All right, and here is always positive, so this term is always positive. But this part, I don't know if it's positive or negative. I don't care, because x is always less than or equal to ups value of x. I always have this inequality. Okay, so this part, I have no idea if they are positive or negative. It does not matter. Okay, so we show the equivalence, but remember that the equivalence has a condition: f to be bounded. F has to be bounded. Okay. The Riemann sum convergence does not require f to be bounded, but the Riemann integral, that using the upper sum and lower sum, it requires a boundedness. Yeah, 19, not 20, 19, 19. 5.19 says sometimes if you have a complex function, you can decompose it into the arithmetic combination of simple functions. So it's the linear property. The linear property says if f, g are integrable, on a b, and alpha in R, then f plus g and alpha f are integrable. On a b. In fact, we have the linear property. The integral of the sum is equal to the sum of the integral. B, the integral of the multiple of a function is the multiple of the integral of the function, scalar multiple. Okay, you can factor out the coefficient. Okay, so we're going to prove this simple property by the definition. It's not difficult, but it's a good practice for all of us. So let epsilon be greater than 0, given epsilon, and because f and the g are both integrable, so there is a partition p epsilon such that for any partition p finer p epsilon and any choice of tj in xj minus 1 xj, we have the ups value of sigma j from 1 to n f tj x minus xj minus xj minus 1. I'm sorry, minus the integral from a to b fx dx. Remember, we already showed that integrability implies the existence of if equal to this number. It's less than epsilon. And sigma j from 1 to n g of a tj xj minus xj minus 1 minus integral ab g of x dx less than epsilon. First of all, this partition p epsilon is related to f, and you should, directly, strictly speaking, there's a partition p epsilon prime related to g. You have two functions, you have two p epsilon, but you just put those two p epsilon together, you join those two p epsilon together, then you will have a common p epsilon. Okay, so that's not the big deal, but strictly speaking, the p epsilon you should have one p epsilon for f, the other one p epsilon for g, but you join them together, you will have a common p epsilon for both. And because this tj is a random arbitrary choice, so you can select tj for both, working for both functions. Okay, you don't worry if they're equal or not equal, so you can select them to be equal. Okay, all these conditions come from the sentence f and g are integrable. And then let's check then this one, the integrability of fx plus gx. It's a sigma j from 1 to n ftj plus gtj times xj minus 1, and minus, we're going to consider these two quantities, integral fx dx and minus integral gx dx, F's value. We're going to claim the sum of them is equal to the I of f plus g. I of f plus g. Okay, then by the triangle inequality, you have such thing. And each of them is less than epsilon, so add them together, you will less than 2 epsilon. Right? So that's what we can prove. For every epsilon, there is a partition such that for any partition finer than p epsilon, and for any choice, you have the ops value of the difference less than 2 epsilon, twice of epsilon. So if plus g exists, and if plus g is equal to if plus ig. This is minus, you see, if I put here, this is if, this is ig, and that's exactly the relation A, right? The relation A. Okay, good. Now let's see the relation B. Relation B. The relation B is even simpler, because when you have ops value j from 1 to n alpha ftj xj minus xj minus 1 minus integral ab fx dx, but it's not enough, we multiply by alpha. Okay, and then you can factor out alpha, sigma f of tj xj minus 1 minus integral fx dx, right? You just factor out alpha, and this one is less than epsilon, so So it's less than alpha ops value times epsilon, and that's it. That is the proof, right? So I don't care if I really have the coefficient 1 for epsilon or not. With any constant coefficient, it will work. Okay, so the proof is done. And what we know is I alpha f. You see, this will converge to I of alpha f. It is equal to alpha times I of f. Alpha times I of f. Right? Okay. So this is a 5.19. So the linear property. Linear property. Now let's see. Sometimes this part we try to decompose a function, and we can also try to cut the interval. So if f is integrable on AB, then f is integrable on each subinterval CD of AB. So if you are integrable over the large interval, you will get integrability over any smaller interval. And moreover, we have the integral from a to b fx dx, the quantity equation. It is equal to the integral from a to c fx dx plus integral from c to b fx dx. For all c inside AB. So you can just integrate function over the AC and CD, put them together, it's an integral from A to B. That's what this theorem says. And when function is integrable over AB, it will be integrable over AC and CB. So the property does not matter. The property is guaranteed by the first part of the theorem. Okay, now let's see the proof. The proof is just the practice of the definition and the equivalence property. So here we assume that A is less than B. If A is greater than B, then you will have the negative sign. All the places you will have negative sign. Okay, so f is integrable over AB. So given epsilon greater than 0, there exists a partition P of AB such that UFP minus LFP is less than epsilon. UFP minus UFP minus LFP is less than epsilon. Okay, so this partition is there. Then let's see. We choose P prime be P union C and D. If P already contains C and D, then you do not include any more point. If it does not contain C and D, you just add join C and D to the partition, and then let P1 be the P prime intersect C and D. We do just want the partition over the subinterval where C less than D and CD is a subinterval of AB. Could be equal. Okay? Anyway. Okay, so remember the partition. What is the partition? So the UFP1 is going to be, because of sigma ftj xj minus xj minus 1. Okay, this is a this xj minus 1, they only belong to P1. So what we can see the following thing. The UFP1 minus LFP1. UFP1 minus LFP1. It's going to be less than what? Okay, no. Yes, it's going to be less than or equal to UFP prime minus LFP prime. UFP prime minus LFP prime. Why? It's because this P1 is a subset of P prime. So you see here, P1 is P prime intersected with CD. So P1 is subset of P prime. So this UFP1 minus LFP1 is equal to sigma, this mj. Sigma mj minus little mj xj minus 1. Here, xj belong to P1. And this is a positive, greater than or equal to 0. All the terms are greater than or equal to 0. But if we choose xj from even a larger set, so it's less than or equal to sigma xj belong to P prime, mj minus mj xj minus 1. Every term is a positive, so you add more positive product, so the sum is also positive, greater, right? Bigger, you enlarge it. Okay, so this is the reason why it is this difference is less than or equal to this difference. And the second, here the P1 is a partition over CD, so the P prime is a partition over AB. And then for the partition over AB, you have a finer partition, you have a smaller the difference. This is a partition over AB, this is partition over AB. This is because P1 is finer than P. Maybe equal, because P1 is a P union C and D. If P1, if P contains C and D, these two things are equal. If P does not contain any of them, you will have less than or equal. Okay? So these are two different properties. So you see here, these two inequalities are consistent, though they share the same direction. And then this difference, remember where is it? Here. The difference is less than epsilon. So what we have? We have the upper sum fp1 minus the lower sum fp1 is going to be less than epsilon. It is less than this, and this one less than this one less than epsilon. So for any epsilon, you can find a P1 such that this difference is less than epsilon. Then f is integrable over CD. Arbitrary subinterval. Arbitrary subinterval. It's going to be integrable over C and D. Okay, so that's the first part of the statement. Okay, now let's talk about the quantitative part. We're going to chop the interval into two pieces. Okay, so let P be a partition of AB. P is a partition of AB, and P0 be P union C. Remember, we're going to insert a point. So P0 is a union P with a C, and P0 including C. And then this is P1, this is P2. And P1 is P0 intersect AC, and P2 is P0 intersect CB. So P1 is a partition on the left hand side, P2 is a partition on the right hand side. Okay, so what we have a P0 is P1 union P2. P0 is a P1 union P2. Okay, now let's check. The upper sum is decreasing with respect to the partition. So P0 is finer than P, so it's decreasing. P0 is finer than P, so it's decreasing. And P0 is a union of two parts, so it's equal to the sum of the two upper sums. Okay, that's one thing. And each of them, remember that we already know the function is integrable over AC and the CB because they're both subintervals. So whenever you have such thing, then the upper sum, it has the infimum. Upper sum is decreasing, infimum is greater than or equal to the upper integral of AC fx dx plus upper integral of CB fx dx. Okay, and because they're integrable, so you can drop this upper sum symbol. So it's just integral from A to C fx dx plus integral from C to B fx dx. Okay, just because fx is integrable over those two subintervals. So what do we have? We have this in. This upper sum fp is going to be greater than or equal to this. Upper sum fp is going to be greater than or equal to this. And this inequality works for all partition. Works for all partition P of AB. So we are computing the infimum. So we have the upper integral from A to B fx dx is going to be greater than or equal to AC fx dx plus integral CB fx dx. Okay, so if it is a lower bound, then the supremum will be greater than or equal to all the lower bound. And because f is integrable, so you can drop this upper sum. So we have upper integral. So we have this one, right? Because f is integrable, so the upper integral is equal to the integral. This comes from the analysis of the upper sum. The analysis of the upper sum. We are going to do the similar argument and get the argument for the lower sum. And here we're going to keep the setting. P, P0, P1, P2. The setting is fixed. We only discuss upper sum and lower sum separately. Okay, the lower sum is this one. The lower sum is increasing with respect to the partition. You have a finer partition, the lower sum increase. And then this is equal to P1 LF P2. You just get the lower sum for the left side, the lower sum for the right side, add them together, you will get the lower sum for all the parts. And then the lower sum is increasing, so it's less than or equal to the lower integral AC fx dx plus the lower integral CB fx dx. The lower sum is always increasing to its supremum. And because they're both integrable, so it's equal to AC fx dx plus CB fx dx. Right? F is integrable. Integrable means they're equal. And this inequality works for all partitions. So the lower integral fx dx is going to be less than or equal to the integral from a to c fx dx plus integral from c to b fx dx. And because f is integrable, so this is equal to integral fx from a to b fx dx. This is because the same reason, because f is integrable. Over AB. Right? So you just get the stuff. So this quantity is less than or equal to the sum. This same quantity is also greater than or equal to sum. Hence, this quantity has to be has to be equal to this same sum. Okay. So these are the standard trick. The standard trick. Okay, so we do show that we can decompose the function. We can also divide the domains. All right, so that's the basic properties about the Riemann integral. And whenever you see integrability, they work for the bounded function. If you want the Riemann sum converge to the IF, that part, we don't require the bounded function condition. Okay, whenever you see the upper sum, lower sum, you need F to be bounded. Okay, we finish this video and we'll continue in the next video. Thank you.